Now, down here, see fx dx xi to xf means initial point to final position. So I took f is equal to minus kx, I took minus k outside and x is inside. So that will become x square by 2. Now minus k by 2 will be taken outside. Xf square minus xi square. Okay, so that's the thing. So how can we write now? So substitute all these values in the formula. So w equal to what? W equal to minus k into x square by 2 minus of minus will become plus k xi square by 2. So w equal to what? Half, you can write half k xi square minus half k xf square. Once again, see here w equal to what? W equal to integration xi to xf fx dx. Now we write minus k x into dx. What is x? X square into x is integration is x square by 2. That will become minus k by 2 xf square minus xi square. So that will become minus k xf square by 2 plus minus of minus will become plus. So you'll get half k xi square minus half k xf square. Okay. So next one. This is the second part. Clear, all of you?
Yes.
Please note down this, then we'll go to the third part. In the third part, we are considering about one cycle. One cycle means we are going from mean to extreme, extreme to extreme, and then coming back to the mean. Now, so we are taking xi to xi, fx dx. So we are writing here minus k into x dx. So x derivation is what? Here we have x is what? X square by 2. So x square by 2, k by 2, take it outside. So that will become xi square minus xi square. So that will become 0. So work done in one cycle is 0. Work done, I'll write the points now. So I'll write the points here. Can I remove this figure?
Yes, sir.
Yes. Yes.
Okay. So I can write few points here. So the spring constant derivation is done. Okay. So how do we calculate if it is a graph is given? Example in MCQ. Okay, to make you confused, they'll just give a graph like this. Okay, so what is this? This is force. Fs, this is x. Origin. So what happens here? This is A. Clear? So what is this? Area under fx graph. See, when f is positive, x is negative. See, this is minus x. X is negative. But when x is negative, f is positive. Sorry. When f is negative, x is positive. Got it? So both are in opposite direction. If f is positive, f minus x. When minus x, plus x. Got it? So if we find out the area under fx graph, I'll write here. Area under, yesterday also we did something. Area under fx graph gives what? Energy, right? Gives potential energy stored in the spring, or elastic potential energy. Gives elastic potential energy. That is which is equal to what? Half k x square. Which is equal to half k x square. Clear? So just it's a triangle, right? Triangle. What is the triangle formula? Area of the triangle. Half into base into height. So half into base into height. Base is what? X. Height is f. So but what is f? F equal to force into displacement. That is f equal to what? Kx. So that will become what? Area equal to half k x square. So this is the formula. Is it clear? Now I want to find out energy somewhere in between, not exactly at the extreme. See, suppose think that this is the mean position, and this is the extreme position, and this is the extreme position. So these two are the extreme position. Now I want to find out the energy at somewhere in between mean and extreme. So there can be both. Here only there is when it is in motion, when the body is in motion. So what will happen here at the extreme point? There is only potential energy, elastic potential energy. At the mean position, there is only kinetic energy, not at rest. Sir, you can ask me, sir, at rest, how can there can be kinetic energy? No. When the spring is moving, back and forth. Okay. When the spring is moving back and forth, in that situation, at the extreme positions, you have potential energy, and at the mean position, you have kinetic energy. But somewhere in between, like I want to find out somewhere in between. So it has both potential energy and kinetic energy at the same, kinetic energy and potential energy, not the maximum. Here, extreme, maximum potential energy. So we can write here, instead of writing maximum potential energy, I am writing here Vm, maximum potential energy. Here I write Km, maximum kinetic energy. Again here Vm, maximum potential energy. So here it has both potential and kinetic energy at the same time, somewhere in between. So I want to find out what is the velocity of the spring mass system. So at the extreme, so what will happen now? Now at the extreme, I have half kx square xm square equal to half mvm square. So this and this will go away. So we get Vm square equal to K by M into Xm square. So Vm equal to how much? That is square root of K by M into Xm. So this is the formula to calculate the velocity. Velocity of the spring mass system. Now, suppose, as I told you, the energy is conserved. Means the energy is neither created nor destroyed, but can be transformed from one form to another form. Here there is extreme, there is only potential energy. Here there is only kinetic energy, but in between there is potential and kinetic at the same time. So what is the formula? Half kxm square. What is that? Half kxm square equal to what? Half ax square plus half mv square. Half mv square. So that will become what? So, so it has both at the same time. Means it has kinetic energy and potential energy at the same time. So it is somewhere in between. This is what? This is somewhere in between. Somewhere in between mean and extreme. Mean and extreme positions. Mean and extreme positions. Okay, half kxm square is equal to half mv square. So v square is equal to k by m into xm square. Cross multiply and remove the root. We'll get the velocity. Where k is spring constant, m is the mass connected to the spring, xm is the maximum displacement. Now what is this? This is potential energy stored in the spring, which is equal to potential and kinetic energy. Clear? Now, any doubt in this? There's a graph here. This is a graph here. So here, 0, this is xm. This is the displacement, x, and this is the energy. So at main position, this is kinetic energy. This is potential energy. Okay. So what is this? E is equal to K plus V. Total energy is equal to kinetic energy plus potential energy. So this is xm. This is minus xm. 0 is the mean position. Xm is the extreme position. Xm minus xm. Okay. So this is kinetic energy. At the mean position, maximum kinetic energy, extreme positions, the kinetic energy will become 0. At mean position, potential energy is 0 and kinetic energy is sorry, potential energy is maximum at extreme positions and zero at the main position. And kinetic energy maximum at the main position and zero at the extreme positions, minimum at the extreme position. So this is the graph, very important. Okay, remember, do this one. Now, next, various forms of energy.
Sir, can you explain the graph?
See, now this is mean position and this is extreme position. So if you look at the kinetic energy, so kinetic energy is maximum here. Kinetic energy is maximum here. And kinetic energy is minimum at extreme positions. Do you agree with this? So this is the graph. This is the graph. Got it? That's a graph. Okay. The second graph is what? Potential energy is maximum here. Potential energy is maximum here. And it is minimum here. Potential energy is maximum here and minimum here. Got it? Is it clear?
Yes, sir.
Copy this, then we'll go to the next various forms of energy. You have various forms of energy. Various forms of energy. So here we have heat energy. Energy due to vibration of particles. Vibration of particles. Or energy possessed by the vibrating particles. You can say in that way also. Next one is chemical energy. Chemical energy is energy stored in food, fuel, and drinks. Next, here we have exothermic reaction and endothermic reaction. Exothermic means if the energy is given out, if the energy is given out during the reaction. That is known as exothermic. Next is endothermic. Endothermic reaction is what? If the energy is taken in. If the energy is taken in during the reaction. If the energy is taken in during the reaction, then that is endothermic reaction. Next is what? Electrical energy. Electrical energy. Energy possessed by the free electrons in the conductor. When potential difference is applied. Energy possessed by the free electrons in the conductor when the potential difference is applied. Next is nuclear energy. Nuclear energy. Energy stored what is that? Nuclear energy, what I can say. It is about the nuclear, about the energy stored in the nucleus of radioactive elements. of radioactive elements. Other than that, we have E is equal to mc square. Albert Einstein's mass energy equivalence relation. Okay, this is mass energy equivalence relation. Mass energy equivalence relation. So we have E is equal to mc square. Where C is speed of light. Okay, C is equal to what? 3 into 10 to the power of 8 meter per second. And is the mass. Okay. So if I am taking 1 gram, E is equal to what? E is equal to 1 into 3 into 10 to the power of 8 whole square. So that will become E is equal to 9 into 10 to the power of 16 joules. Okay. So this is also known as 8,000 megawatt. 8,000 megawatt. Mega means how much? 10 to the power of 6. Mega means 10 to the power of 6. Are you able to see the board properly, girls?
Yes, sir.
The first
Yes,
one,
sir.
heat energy, energy possessed due to the vibrating particles. Chemical energy stored in the food, fuel, and drink. Even if you buy a drink, also it is written 300 kilocalories of energy like that. So in that again we have endothermic and exothermic. Exothermic when the energy is given out during the reaction, and here endothermic when the energy is taken in during the reaction. Electrical energy, energy possessed by the free electrons in the conductor when potential difference is applied across it. Nuclear energy, energy stored in the nucleus of a radioactive element. Okay, and next is mass energy equivalence relation. E is equal to mc square. This is given by Albert Einstein. Other than this, we have so many energies. What are they? Tidal energy, wind energy. There are different types of energies. Okay, so that is not mentioned in the book. So just copy this. We will go ahead with the next. That is power. Power is the rate of doing work. The rate of doing work is power. So now power equal to what? So power equal to work done by time or energy by time. Power equal to energy by time. Next here we have it's measured in what? E is equal to W by T. E equal to W by T. And here we have E equal to W by T. Next one, or also we can write P is equal to FV. P equal to FV. Force into velocity. These are the two formulas. Unit of power is what? Watt. Named after a scientist, James Watt, who invented steam engine. Okay. Joule per second or kg meter square second square by time, right? So when it comes up, becomes -3 kg meter square per second square divided by second. So second comes up becomes -s.